As part of my problem series, in this video I will be analyzing a series parallel AC network for currents and impedances. Once I am finished with this series of problems, I'll be posting them in my stand store at this web address. A series parallel AC network is shown here. Our task will be to calculate the impedance as seen from the voltage source ZEQ and the current flowing in the three branches I1, I2, and I3. Step 1 is to find all of the series impedances starting with Z1, which is equal to 300 plus J600 minus J200, which can be reduced to 300 plus J400 in rectangular coordinate notations, or in polar coordinate notations it is equal to 500 at 53.1 degree ohms. Z2 is easy. It is simply 500 plus J1200, or in polar coordinate notation 1300 at 67.4 degree ohms. And Z3 is equal to 800 minus J600, and in polar coordinate notation it is 1000 at minus 36.9 degree ohms. Step 2 is to combine all parallel impedances. Using the product over the sum rule, we find that ZBC is equal to Z2 times Z3 all over the quantity Z2 plus Z3. Plugging in real numbers, we get 1300 at 67.4 degrees times 1000 at 36.9 degrees all over the quantity 500 plus J1200 plus 800 minus J600. I use polar coordinates in the numerator and rectangular coordinates in the denominator because of the product required in the numerator and the sum required in the denominator, and that gives us this. Converting the denominator to polar coordinates in order to do the next math required, performing division of the magnitudes and subtraction of the angles, gives us 908 at 5.7 degrees in polar coordinate format, and 901 plus J 90.2 ohms in rectangular coordinate format. Step 3 is to combine all impedances. To obtain the total impedance ZEQ, ZEQ is equal to Z1 plus ZBC, which is Z1 300 plus J400, and ZBC 901 plus J90.2, which equals 1201 plus J490 ohms in rectangular coordinate format, and 1290 at 22.4 degree ohms in polar coordinate format. Step 4 is calculate the currents. That we use Ohm's law. I1 is equal to E all over ZEQ, or 1000 at 0 degrees all over 1290 at 22.4 degrees, or 0.0775 at 22.4 degree amps. For I2, we use the current divider rule. I1 times Z3 all over Z2 plus Z3, which equals 0.0775 at minus 22.4 degrees times 1000 at 36.9 degrees all over 500 plus J1200 plus 800 plus J600. I'm not going to go through the coordinate conversion and mathematics. That's a good exercise for you to do on your own. The final outcome is a current that is equal to 0.0541 at 84.1 degree amps. For I3, we again use the current divider rule. I3 is equal to I1 times Z2 all over the quantity Z2 plus Z3, which equals 0.0775 at minus 22.4 degrees times 1300 at 67.4 degrees all over the quantity 500 plus J 1200 plus 800 plus J 600. Again, I'm not going to go through the coordinate conversion and mathematics. The final outcome is a current that is equal to 0.0709 at 20.2 degree amps. Any reducible AC circuit, that is, any circuit that can be reduced to one equivalent impedance, ZEQ in this case, with a single power source, no matter how complex, can be solved in a similar manner to that which we have just described. The DC network theorems used in previous DC problems can be applied to AC networks, except that vector algebra must be used for the AC quantities. I want to introduce you to another product that's out there that is worthy of paying attention to, the 𝐃𝐈𝐒𝐂𝐋 F2000 generator. To find out more about this battery generator and to keep up to date on any sales or discounts that are available, simply go to the Anchor site at this web address. And by using this web address, you can get $800 off the original price, or just browse through the various options on this site. There is no charge for just looking, but you might find something that is available at a discounted price at this particular time. And remember, this video has been brought to you by PSPT, where you will find electrical training videos when you go to this web address, which will also give you a free copy of my 50-page crib sheets that you can use while viewing any of my courses, or just keep it handy during your everyday work.